Thank you, everybody, for coming back. We're going to have a little treat today. We're going to talk about cognitive computing. And I'm going to start off, and then our panel is going to give a little bit of a presentation. And I'll start off with a little background on what is cognitive computing, tell you a little bit about how the human brain works and how we can learn from it, with the caveat that I'm not a neurologist. But we do have one, so Sharif, if I say anything wrong, please feel free to correct me.
Don't worry, I will.
Okay. So let's start with the first slide. Cognitive computing. Okay, so my forte into cognitive computing started because I'm trying to deal with this really complex data. So this is a genome, and with genomics, we have just a ton of data, and I've been working on this for a very long time.
I thought it was a cognitive computing talk and not genomics. That's the wrong slide deck, right?
Bear with me. I'm gonna hold on, Sherry. We'll get there. So no, I'm using this as an example. I know I just gave a talk on genomics, so he's worried that no, this is a cognitive computing talk, I promise. The reason we're looking at genomics is we're trying to apply systems biology. We're trying to make sense of this, and it's beyond our human imagination to try to make sense of this really complex data. There are about 3 billion base pairs.
3.2.
What?
3.2 billion.
Sorry. You know I only have 5 minutes, right? Okay, so there's 3.2, thank you, billion base pairs in the human genome. And so we've been working on ways to understand those genomes and figure out how we can innovate with cognitive computing. And the insight came from the most unusual place. It actually came from Rain Man. So back 25 years ago, I started to think about...
27.
Pardon me?
In 1988, it's 27 years ago.
Come on. Okay. Okay, so 27 years ago, I got really interested in Rain Man. And at that time, I was very interested in how the human brain works. So this is where we're going to start talking about the human brain. Human brain is an amazing computer. It's got 100 billion neurons. And
86 billion.
What?
86 billion neurons about.
Do you want to do this with me?
Yeah, let's just do it together, Spiro.
All right, I give up. All right, let's do this together. Thank you.
That's collaboration right
okay.
there.
Okay, so 100 billion neurons, but they're organized in a very interesting way. They're interested in a hierarchical pattern. And so if you think about the brain, there's, what, 2 parts, right? You want to...
So you have basically this neocortex, which you're seeing on the right side of the screen, and it's this top-down approach with side-to-side connections in each of the neocortical layers. And then each of those networks is actually networked to another part of the brain, which is what we're seeing on the far right side of the screen, which is actually the connectome. And so that's the diffusion tensor imaging that shows all the connections between all the different specialized parts of the brain. So you have these boxes connected to many, many different boxes.
So if you think about the neocortex, it's like a dinner napkin. So if you hold it up, it looks like a dinner napkin. If you hold it to the side, it's about that thick. So what we're really interested in is how data comes in from the bottom, abstracts up, and then creates a network of networks. Okay, so this is a way of processing information that we can learn. So you heard Anthony talk about biomimicry, how we can learn from birds. But we don't want to replicate a bird, and we don't want to replicate a brain.
This is exactly what we were seeing. This is the aerospace of how the brain works. So if we understand the aerodynamics, of how the brain works, then we can replicate that. So we're not trying to create a brain, we're trying to understand the understanding behind how the brain works. And if we get that good HTM, right, this which is the hierarchical...
hierarchical temporal memory.
Yes, thank you.
I got you this time.
There, he's correcting me now. So this hierarchy, if we understand it, then we can replicate it.
Right. So we said again that this idea of doing biomimicry, taking this idea of abstraction, hierarchical layers of information being abstracted to knowledge, and then that knowledge being networked, is a really phenomenal idea, and building computers that work like this has been around for a while. So I first got inspired to start in this field back in 2004 when I read On Intelligence. And since there's been other good books too.
Yeah, the great one to read is How to Create a Mind by Ray Kurzweil. And he really talks about how the brain understands patterns and pattern recognition, and the use of that in natural language processing is where he primarily looks at.
Yeah. There's a lot of other references we can give you, but these two books really cover the topic of how to copy the principles of the brain to build computers. We published on this concept of hierarchical organization of knowledge quite a while ago, and at the time, we didn't exactly know computationally, we didn't know the code, but we had the principles. So we decided to publish these principles and put it out there for how we would do it in biomedicine. So basically, we have a lot of gene data, we have a lot of mutations. It gets abstracted to a higher order function, it gets abstracted to a biological concept, and then maybe some clinical consequence. And so this is a representation. It's called a graph. It looks very much like
the organization that we just talked about, the HTM, right?
Exactly, exactly. And so that's the very simple idea. Let's create knowledge representation strategies that look like this. And the idea is that data would come in exactly the same way, get abstracted to higher and higher order concepts, just modeling exactly what the brain does. Now, along with that, you'll see in the title epistemology. We wanted to use an epistemological perspective because we didn't want to just represent knowledge. We wanted to take a step back and say, well, what is knowledge? So in our human brains, when we have a belief, we create a model of reality. There is no reality in our brain. It's just a model of what we think is real. So when we think about a cell, for example, we have a belief of what a cell does, how it works, how it looks. What we do is then we observe data from reality. We might look under a microscope, we might collect other type of data, and we test that belief, or we test a model, or we test a hypothesis against that reality.
And that's when we realize that in the middle is knowledge, and that's when the Earth is not flat, it's actually round, and it rotates around the sun, not the other way around.
Exactly. And so this is not a new idea. So Plato famously said, knowledge is a justified, true belief. Think about how profound that is. Knowledge is a justified, true belief. What that means is we believe things that come out of our imagination. We test them against reality with data and with big data, right? And then from that big data and testing, we come up with what we believe to be knowledge, what we know, and that keeps evolving. So the question that we ask ourselves is, well, if knowledge starts as a belief that comes from the human imagination, what if we had machines that can imagine? And that's where we're going to come back to what
that movie, yeah, 1988.
That's right. So if you think about high-performance computing and natural language processing and machine learning, high-performance computing and Wikipedia, you get Watson.
Which is basically Rain Man.
Or Sharif. So Rain Man could absorb a lot of knowledge. In the movie, Rain Man, who was autistic, had the ability to ingest information and regurgitate. What's fascinating is that Rain Man actually exists. There's a gentleman, his name used to be Kim Peeks, he's passed away since, but Kim Peeks was an incredible human being. He'd read phone books and regurgitate them. He's able to understand very little of what he read, but he remembered everything.
So the beauty of his brain is that his neocortex was so hyper-connected. But if you actually look at his brain, and you look at a normal brain, there's actually something that's very interesting. It's actually misformed. And there's a giant bundle of fibers labeled the corpus callosum, and he doesn't have that. So he has these networks which are really, really efficient at pattern recognition and storage of information, but those networks are not talking to each other and they're not connected.
What's a corpus callosum?
That's the bundle of white fibers that connects the two parts of the brain, and we have a nice picture for you.
So can we think of this as a network of networks?
That's exactly what it is. It is the network of networks.
So the neocortex would go around this, and you can actually trace, and this is an actual image from a human brain, you can actually trace one of these lines to another part of the corpus callosum. And that interconnectivity, that connection of ideas, that's what Kim Peeks was missing. This is why Kim Peeks couldn't live on his own. If you ask Kim Peeks how much does a chocolate bar cost, he'd say, I don't know, $50? Because he didn't have that knowledge. Nobody taught him that. This is what our databases are like today. They don't form any new knowledge. They just regurgitate whatever knowledge we find. So if we now use that back to biomimicry that Sharif was talking about, this is our aerodynamics. We know that data comes in. We know we can create hierarchical structures to capture that knowledge. The next question is, how do we form these beliefs and imagine new models that don't exist so we can create new knowledge? And the answer is the network of networks. We need something that can do this, but can also do this. Because as Albert Einstein famously said, imagination is more important than knowledge. So this is where I came into going from theory into something practical. So we developed a framework. We called it the Biointelligence Framework. And when I say we, I really mean very talented computer scientists that took these crazy ideas and turned them into code, something that a computer can understand, a data model. And I don't have enough time to talk. How much time do we have?
You're way over.
Yeah, so we don't have time to talk about the technology, but suffice it to say that we've been able to achieve both storage of knowledge and imagination. So with that, what's the goal? What does 2040 look like? Well, I know that Watson can beat me at Jeopardy. I challenge Watson to beat me at systems biology. And I think by 2040, we'll get there.
Definitely. Time to imagine.
Okay, let's go to the next one.
Good morning. My name is Paul Barish. I'm a surgical intensivist, cardiac anesthesiologist, and I've been using social sciences for the last 20 years to better understand the cognitive performance shaping factors. 20 years ago, I was in the military for 5 years, and what I studied back then was how human factors shape the ability of individuals and teams to perform reliably. We are a highly unreliable healthcare system today. We kill about 50,000 people in the US every year. We maim about 500,000. Despite all the technology and everything we've talked about, the performance shaping factors of fatigue and noise, distractions, haven't really changed in 1,000 years. The computational cognition aspect of my pivot here is, what are the performance shaping factors in which these technologies are going to work ideally? This is human factors, and human factors includes cognitive, artificial intelligence, statistical design, and ergonomics. These are frameworks for understanding the physical environment. The room that you sit in shapes the quality of your decisions. How much alcohol we had last night shapes my ability to not slur words right now. And we drank a lot, thanks to Dr. Wetzel. I'm going to call him out. But most importantly, we've better understood that we can get teams to perform more reliably if we use these performance shaping factors. The most important book on this topic, Donald Norman's book, Imagine If You Poured Coffee This Morning. We've designed healthcare systems right now to harm patients, but more importantly, they harm providers. We know a lot about how poorly designed systems, 80% of harm in healthcare is due to poor systems, although they're human errors that are led by systems. So the expediency around innovation is building on the last 15 years of political drivers supporting and funding safety and quality drivers. If you apply the innovation platforms using human factor tools, you can dramatically get your management to support these ideas. Here's a great example of a patient who was harmed because of a routine ophthalmological. They both look alike. One will kill you, and one just makes your eye better. This is like putting poisons and vitamins in your bathroom and hoping not to take the wrong vitamin when they're not labeled differently. This is a model on how we look at how people are harmed. So when a child is harmed with an infection, a fall, or a wrong-sided surgery, these models of human factors give us tools and frameworks to understand how to enable them to do the right thing and not do the wrong thing. And we're talking about a load of about $5 to $10 billion a year just in the US, around the world. It's hundreds of billions of dollars. So as we progress with innovating new technologies, understanding these frameworks, how people behave when they're fatigued, how they share information, how they deal with cognitive errors. Can they speak up? As you probably know on the NASA Challengers, what killed the Challenger program was not the technology, it was the culture. Imagine that for a moment. Culture can kill technologies. What is the role of culture in enabling these technologies to get in place? Not just the bytes and bits, but the culture around the bytes and bits. Here's an example. We've been working a lot on alarm fatigue. The number one problem in the US, according to the Joint Commission, is alarms that don't talk to each other. 95% are false positives, equivalent to the 99% of false positive alerts on health information systems. This is killing providers. 30% of the time they're turning alarms off because of a lack of integration between hardware, software, and firmware. And it's a very complex issue of, again, using human factors to design better alarms to gain your attention but not cause you to turn the alarms off or not cause you to assume what we call the normalized deviance, where everybody assumes that the alarms are mostly false and therefore positive information doesn't get through cognition. So I want to wrap up by really identifying this issue of, when we talk about cognitive computing, what are the cognitive loads that these technologies impose on providers? And how, in this innovative design framework over the next decade, how do we design environments that impose less of a load, that allow providers to reflect more on their work using a variety of narrative and social technical aspects? Because at the end of the day, this framework is how other domains and other industries have become so safe for the last 50 years. So aviation, nuclear power, all the industries that we've talked about here that outside of healthcare use human factors. How many of you actually work with human factor experts in your organizations? One hand, two hands. Okay, if there was any other industry in this room, every hand would go up. This is standard practice, but not in healthcare just yet. So my final comment is, in order for healthcare to be highly reliable, which is a framework that all other industries use, we must introduce human factors, tools, techniques, and frameworks to better understand how do we support innovation, and most importantly, support the providers who are struggling with these burdens of information, knowledge, and systems. Thank you.
Fantastic, thank you. Quick 15 seconds. I was going to point to Sharif. This is fantastic. I think we should all be doing this. Our biases. I mean, humans have biases.
So in addition to all the fatigues, what do you think about the cognitive biases that we all hold?
Huge.
Yeah. Do you think that there's an opportunity to also use the technology to identify the biases and present them to the patient or the provider or whoever is doing the human factor?
Yes, as long as they're coupled with behavior modification. So it's a social technical problem. It's the social part of that equation that's the problem right now. So the challenge with just designing technologies without addressing the social aspects is that you undermine the cognitive repair mechanisms that are out there. So technology has a huge part here, but for example, transitions of care, the number one issue that Medicare is focusing on, the most important issue is not the technology, it's the fact that people don't follow the technology and don't listen to the technology. So how do we get those humans to understand the limitations of the technology so that they can perform more reliably?
Challenging questions. Let's go now to James.
Good afternoon. My name is James Desanowski. I'm going to talk about cognitive computing and specifically the issue of knowledge representation. So when you go through medical school, you have this book called Guyton about that thick. You have EKG data, that's data, clinical data. Then you have experiential knowledge, and you have to put all this together and reason on it. And we think very well symbolically. We can talk about ST segment elevation, and that implies something about an infarct. So we think at that level. So we have to bring all sorts of data, whether it be vision, natural language, and pull it together and reason symbolically upon it. So that is really the issue, is how to represent knowledge. So imagine if you had a knowledge-based system that was very good at cardiology, one that was very good at cancer. You could actually, with a unified knowledge, have these communicate through some sort of knowledge highway and have cooperative knowledge-based systems interacting and sharing their expertise upon demand. So really, I think it's an integration problem, and we have to think about how we can unify how we think and capture reason and then make decisions based upon that.
That's fantastic. We talked a lot about cognitive computing. We talked about the human factor. Talk to us about security. You're an expert in AI and security. Is it going to get harder to secure these types of systems?
Actually, I think it's a lot easier because the more data that you have, the better you have visibility into the environment. Take, for example, biomedical devices, which are about the worst from a security point of view. But if you have good sources of information about that, you can see if someone has taken over the device and doing nefarious activities and then exfiltrating data out of your environment and causing you HIPAA fines. So it's actually an easier problem because you have more data and greater visibility.
Well, that's a wonderful point. I mean, if you think about it, cognitive computing can actually improve security. You create situational awareness, you create content awareness, and now you can better secure the systems.
Absolutely.
Yeah.
So if you have visibility, you can, the world is far more complex. It's just not a mainframe anymore in a data center. You have, everything's connected, and the perimeter is now the individual. It's not a data center with the building. So you have to understand the world going on there. So you have better visibility.
Wonderful. So next, let's switch to how we might interface with all of this. And
Yes, hi, I'm Nardo Manaloto. I'm a product guy, and basically I'm the lucky guy who gets to integrate all these cognitive computing technologies across the board. So in ways of background, I've created digital avatars for several companies with different cognitive computing capabilities, one being with IBM Watson and another one being with an AI engine coming out of JPL NASA technology. And they were made for senior health and wellness. And these are systems that are digital avatars that can do Q&A, that can do assessments, that can observe your symptoms, look into medical devices and capture those kind of data. And based on that and applying all those different technologies, here are different things that I found as I implemented these systems. One is there's definitely a massive amount of data, not only from just capturing, but it also generates other data. For example, if I try to do a sentiment analysis on a particular NLP type of text, then basically I'm generating more tags and more data behind the scenes. The other piece is the context, the linking and the contextualization of the data itself. I need to make sure when I converse with these systems that I'm trying to make the conversation link together in a contextual manner, so I don't get a patient into a patient safety scenario whenever they're having a discussion with an avatar. The other piece are the massive amount of algorithms that needs to get changed. So, for example, how do you create an emotional model to capture whether a patient is happy, is sad, is disgusted, and so on and so forth. So there's an entire model for an algorithm that creates an emotion model. The other piece, building the knowledge base and the knowledge graph in itself, right? So there's what we call domain-specific things that you could do. Let's say senior health is a domain-specific thing. But once you get into disease-specific applications, let's say diabetes, then all of a sudden you go into heart disease. You need to make sure that the domains somehow are bridged together and work together, right? So for example, if I ask an avatar and say, hey, avatar, can you give me my symptoms? And you have two domain-specific things in there. Well, what symptoms are you talking about, right? Is it about the heart disease or is it about the diabetes? So you need to make sure that you have that capability of linking and making things in context. The other one is making sure that the training aspect of this is as well, training the avatar to, let's say, recognize mistakes, recognize keywords, recognize patterns of symptoms, recognize patterns of audio itself in terms of, let's say, Parkinson's disease, voice modulation, and voice signal processing. Those are things that all needs to be behind it in order for this kind of things to work. And then lastly, a lot of it, there's definitely a lot more here, but in order for this to really happen, I see this technology becoming a digital representation of you, right? Because it's going to be the next generation EMR, PHR, where all that data is linking towards your particular context.
wonderful. A digital, go ahead, yeah. A digital representation of you. Let's pick up on that because I think that there's something really special there. Anthony Chang, who we affectionately call Dr. AI, famously said that AI should be invisible and omnipresent. You're saying that not only that, let's go beyond, let's have a representation of you in cyberspace that I can interact with. How does that work? What do you, I mean, do you envision by 2040 that there will be some representation of us floating around the ether space communicating, so my representation can go talk to Sharif's and set up a meeting or something?
Yeah, so when I say digital representation, we're looking at all the digital data kind of contextualized to you, right? If you look at what you have now, EMR, PHR, that's you in itself, right? All your social activity, that's you. All the medical devices that support you, that's you. All the interaction that you have with your family and friends, that's you. So all of that, right, if you look at what we're doing with mobile devices, tablets, and all that stuff, it's generating all that data. So eventually, what if we can harness that into a single representation? Let's say an avatar, right? And say, I could do things like, okay, let me model a particular drug therapy through your own digital representation and see what is that reaction from a data standpoint. So that is what I meant by digital representation.
That's wonderful.
So I think if I had to say what the take-home point of the cognitive computing session would be, is not just about what the computers do and how do we establish cognitive computing, it's just as much about how we as humans interact with that cognitive computing.
Well said. Is there anybody in the audience that has any last comments? We have just a few minutes left. We can take maybe one or two quick comments or questions. Did you have something?
I just want to pick up on what Sharif said. I think the context in which the technology is performing is hugely important. We tend to assume that the technology is free of context, but in fact, a lot of work from other domains suggests that by looking at the environment, the physical and organizational environment, we can enhance the reliability of the technology to deliver on its promise. However, if we ignore that, we tend to lose a lot of its value because people don't listen, because they don't talk, because they don't tell the truth, because the environment undermines the reliability. And so it's the ability to amplify the impact of technology by understanding how the context around the technology can add the value that the technology promises.
Let's take a question in the back. Yeah.
So it's probably unfair to ask this question because it's so fresh, the whole process. But I can see a lot of similarities to what happens in radiology in the sense that this is so high-tech, pretty complex. Now, if I'm going to use this in practice, it's going to need validation. And good validation with good science behind it takes some time. By the time the technology has already moved on and gone to the next iteration. So what is your plan for seeing this in practice without spending a huge amount of time validating it so that it's robust enough to overcome the skepticism of clinicians?
No, I think you're right. It is unfair to ask that question.
Actually, I have a comment on that. I worked on a system called the Authorizer's Assistant. It did real-time credit and fraud decisions for American Express. So when you swipe your card, it often would go to this knowledge-based system to issue credit or detect fraud. So your validation was key because it was automated. So there's nothing about Wall Street people that gets more serious about them as money. So there's going to, so they had to trust it to the point they're going to give you this charge. So it had to be fully automated. So one of the things is that we worked on is it validates the way it came up with the decision as much as what the decision was at the end. So you validate the line of reasoning. So you look at how you think through differential diagnosis. You look at, you talk about how you go through that process. So you have to validate the internals besides the ultimate answer. And we built systems to do that.
Another interesting corollary to that is as CMS has been using more technology, the number of detected fraud has gone up 5-fold. I don't think the amount of fraud has gone up 5-fold, but the technology is surfacing things that look like fraud. In essence, they're bad rules. But the dangers of technologies that are not mitigated with the context is that suddenly there are all this identifiable fraud, but it's not really fraud. And so how do we understand that as we apply these sophisticated data mining tools, we understand the limits of the humans that are putting in information, don't understand the rules, and are labeled as fraudulent? They're not fraudulent. They're bad organizational systems that set people up for failure.
Yeah, the other point to make about evidence is that we are in a, I'm going to steal a term from Anthony if he doesn't mind, intelligence-based medicine. I mean, we are all focus so much on evidence-based medicine, but the reality is this thing that we call evidence is just knowledge. And as I pointed out, knowledge is just a belief that's been justified by some data. If you modify your model, you may be able to justify a better model with the data, which means that knowledge is not this static thing that you go and find and hold on to. It's this evolving thing that we have to get past this idea that there's some truth and evidence, and once it's been codified by a clinical trial, then that's what we should do for the next 20 years, right? I'm looking at Lenny Sender, and he lives this. Is the state of the art of cancer treatment is not something that you want to adhere for the next 10 years. It has to evolve on a weekly basis, and we can't wait 20 years for that type of evidence. Cognitive computing is a mechanism by which we can test not dozens of models, but billions of models a second against big data and rapidly evolve what we call evidence. And so moving towards intelligence-based medicine means that let the data tell us what is a justified true belief, not what 10 years of historical treatment without testing has been. So do you want to comment on that, Lenny? No, I said it, okay. So anybody else in the audience? Yeah, we got one right there.
I really enjoyed this session, just the way that you present the human mind and how amazing the computation ability is there. It's light years ahead of any technology we're trying to develop. And then you're mentioning that we're also trying to develop this technology. I enjoyed the part about human factors. How do you use the human mind as it is right now and leverage current tools that we have to extract as much power as we can out of our human factors, and then marry those to the new technologies that we're doing? There's some technology that's already done this. The iPhone has been very successful. So the interface is very important. How do you see this future, and how do you see we can impact medicine to achieve the goals that we want to?
It's a really good question. There's great opportunities there, but there's also, like Superman says, great risks. The unintended consequences of poor interfaces, given human nature, can be not particularly beneficial for the child, the parent, or the system around them. And I think it's a better understanding of the social lenses and how people interface with devices, with information and decision making. And there's a lot of work from a variety of social science methods that can be used to better understand how the technologies can be more quickly adapted and designed to the constraints of human knowledge and human behavior. Because that's what we're talking about. Human cognition hasn't really changed in hundreds of years. The interfaces we can understand now, and they can be applied to rapid cycle technology innovation as opposed to waiting until you go through all the various erroneous misrepresentations by humans because of the systems in which they're forced to live within.
That's right, and we're not really light years from this. This will happen in the next 25 years. We will see computers that work very much like brains, but at the risk of being interrupted by Sharif, I'm going to let him explain what some of the biases are. What are some examples of biases that the human brain has that might come through when we build computers like brains?
I think the way that we have to watch out for biases. So the one that probably the biggest one that we see is often anchoring bias in medicine. That's when you see something, you think that that's what it is, and despite new information coming in, you don't readjust your thought patterns. So you get fixated or anchored on a specific diagnosis. My individual human brain, any one individual human brain may not be powerful enough to understand how the human brain works, but our collective minds and leveraging the technology that we have should and will be able to understand the human mind and replicate that.
Thank you. And with that, you have one last comment?
Yeah, just one last comment on that. In line of my work, what I'm always looking for is observation data, where you could already classify what is correct and versus what's not, right? So from a machine learning standpoint, we hardly have that right now, right? So from a human factors perspective, for how you could deal with cognitive biases, you need to have that as a base infrastructure for cognitive computing in order for this to work properly.
Yeah, well said. So the future is bright. Thank you very much.